Okay, so please give your attendances in the chat box and begin today's class. So, since in the last class, some of you expressed that you might not be familiar with the concepts of generalized coordinates and constraints. So, I have decided I will have a very short discussion on that, what it means essentially to have constraints and how can suitable choice of generalized coordinates help us in taking into account those constraints. Okay. So all right. So first of all, let me discuss constraints. Okay. And so constraints means that if you have to describe the dynamics of a system of particles, first thing you usually do, you just draw your Cartesian coordinates. And so if you have, say, n number of particles in 3 dimension, n number of uh, particles in 3D, you would say that you need 3n number of coordinates. So, so 3n number of coordinates. By coordinates, I implicitly imply Cartesian coordinate. Okay. Required to describe them. Okay. Now, constraints mean that not all these coordinates are independent. So, constraint. Suppose the distance between any two particles are constant. Okay. So then you so distance between any two particles, suppose the ith and jth particles are is a constant, so that will be that can be expressed by, so suppose the distance between ith and jth particle would be xi minus xj whole square plus yi minus yj whole square plus ji minus zj whole square. The square root of this thing is equals to a constant, let's say 2 or 3, depending on that. So this kind of things leads to a constraint. So that means that this xi and xj are not independent. So if you know the position of the ith particle, you can somehow get the position of jth particle, like and it's arbitrary up to a surface of the sphere, but you see, given the position of the ith particle, the choice of coordinates for the jth particles are not completely free. So these kind of things would be called a constraint, and you can also formally write it down as Ri minus Rj is equals constant, right? So the general idea is that suppose you had this n number of particles in 3D with coordinates. So the coordinates would be given by, say, R1, R2, R3, dot, 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 and up to Rn. And you write down constraint equations like this. Suppose, so in general, I express this as F1, R1, R2, up to Rn. Say, actually, it can also depend on T in general. That equals constant. So this is my, so this one implies this is my first constraint equation. I can have further constraint equation. So f2, another function. So I call it c1, say r1, r2, then rn t equals, so c2. Okay. And things like that. And suppose I have the mth constraint equation. same as a Cm. So these are, say, M equation of constraint. Now that means from each of these equation I can express one of the coordinates, one of these Cartesian component, as a function of the others. Okay. So now what I do is that so since those are dependent variables now, since those are no longer independent, I can say my number of independent variables that are remaining, independent coordinates that are remaining, are basically the original ones minus the number of constraints. You know this, and this thing is called the degrees of freedom. So I will call this thing f, or let's say small n, and I call it degrees of freedom, okay, of the system of particles. Okay. So these are the number of independent coordinates that can be chosen. Okay. So there are many types of constraints by anyway, but this particular set of constraints, when it can be expressed as these kind of equalities, these are usually called holonomic constraints, and in our courses we will particularly focus on this thing. So whenever I say constraint, I implicitly imply that these are holonomic constraint, and these have two more subclasses depending on whether it explicitly depends on time or not. Okay, that's not that will not be very useful for our discussion. So, but whatever can be expressed as an equality, you can express the dependent coordinates in terms of the independent coordinates. Now, actually, what you can do, you can go one step further. Okay. You go one step further to say, suppose, since I have this n degrees of freedom now, so I can have n number of suitably defined coordinates that I denote by, say, q1, q2, up to qn. Okay. And this r, since I had since I have already had n degrees of freedom, so I can wisely choose. So this is the term. This is like wisely chosen. Okay. This doesn't fall from tree. Okay. So I can choose this n number of free things here, and I can express all these R1, R2. So R1 equals a function of these things. So Q1, Q2, up to Qn, in general T also. And say Rn is also a function of Q1, Q2, Qn, G. Yeah. Now I can express that. Okay? So if I can express that such that, so I already told you that these are wisely chosen. Okay, so what do I mean by that? So wisely chosen, so such that the constraints are taken care of by design. Okay, so this is very important. So I choose Q1, Q2 up to Qn, Q small n, such that the constraint equations are taken care of by design. I choose Q1, Q2 in such a way that I do not have to think about the constraints anymore. So let me put it this way. I don't have to think about the constraints anymore. I will give you one example. How can I do that? But if I can do that, I will call this Q1, Q2, these things as my generalized coordinate. Okay. Now, to give you an example, consider a particle moving in two dimensions, and this is constrained to move on a circle. Okay. So let me draw a circle first. Suppose this is the circle, and this is somewhere is the center. Okay. This is a circular ring on which a particle is constrained to move. All right. Let's say, and the particle is somewhere here. And the particle's coordinate can be, so there is one particle, let's say. So I would say, I call it say x1, y1. That is the coordinate of the particle. Now, so basically the coordinate of the particle would be r1 equals x1 x cap plus x2 y cap. Okay. But since it is constrained to move on this circular ring, suppose I have created this circular ring and I have put the particle on that. So I know that, sorry, not x2, this is, I guess, it is y1. Okay. So I know that the coordinates of these things, so x1 and y1, there are the 2 degrees of freedom that we would expect, but it satisfies x1 square plus y1 square equals, say, a square, if a is the radius of the circle. Okay. So it satisfies this thing. Okay. Or if you prefer to express it in terms of this r1, you can write down magnitude of r1 equals a. R1 dot r1 equals this. Okay. So this can be taken as your constraint equation. So this is similar to this equation. Yeah. Okay. So that tells you that this x1 and y1 are not independent. Okay. So you can express, say, y1 in terms of x1 as, so y1 would be square root of a square minus x1 square. And then wherever you encounter y1, you substitute this and you calculate. That is one way of doing things. Sure. So you just express everything. But that usually is a bit more cumbersome. A more elegant way of doing it is that you redefine your coordinates such that your constraint is taken care of automatically. Suppose if I define, okay, so if I define x1 equals a cosine theta and y1 equals a sine theta, so this a is a constant, I can see that by this definition, this equation is automatically satisfied. So if I define my x1 and y1 in such a way such that my constraint equation is automatically satisfied, and I see on the right hand side I have only one independent parameter, that is theta. Okay. So I will call this theta to be my generalized coordinate. Okay. And then proceed further. Okay. So now, so this theta now becomes my generalized coordinates. Notice that this theta is a dimensionless quantity. So you see, the generalized coordinate doesn't need to have dimension of length. Now you can express everything in terms of this generalized coordinate, and you work with this generalized coordinate. Okay. For example, the kinetic energy, which in the case of old coordinates would read half m x dot square plus y dot square. Okay. Or we can sorry, x1 dot square plus y1 dot square. What you have done is that r1 dot r1 dot. So this was the kinetic energy. Now remember, I told you that if I go to a different coordinate system by doing this kind of transformation, then this kind of transformation is equivalent to this. Okay. So this q1 is basically your theta, or you can call it theta 1. Okay. There is only one generalized coordinate here. Now if I try to write down my kinetic energy in terms of this, last time we encountered expression like this is summation over del. So if there are many r, so let me remove the summation. If I have only one r, so that would be del r1 by del qj del r1 dot del r1 by del qk, I think qj dot qk dot. Somehow this was my expression, I guess, if I remember correctly. Might be a half here. Okay. Now, if I now evaluate these things, so I have only one q, right? That is just q1 equals theta. So this just reduces to half del r1 del theta dot del r1 del theta uh, times theta dot into theta dot. So theta dot is theta dot square. Now let me find out what these quantities are. Remember, so r1 I defined as x1 x cap plus y1, sorry, yeah, y1 y cap. And this x1 is, as I said, this is a cos theta x cap plus sine theta y cap. Now, of course, del r1 del theta you can calculate from here is basically minus sine theta x cap plus cosine theta y cap. Okay. Now I have to compute this. So del r1 del theta magnitude square. So that gives me a square sine square theta. So this is a square sine square theta plus a square cosine square theta times theta dot square. So that just becomes half a square theta dot square, which is what you should expect, right? So you remember in a two-dimensional polar coordinate, the velocity expression for velocity is r dot and r theta dot, but here r dot is 0 because my radius is a constant. Okay, so only thing that survives is the motion along this direction. Okay, so that here tells me which is just a square theta dot square. That's my kinetic energy. Perhaps I missed m here, so I forgot to carry forward. So this is how you do things with generalized coordinates. So notice the important stuff here. I have chosen a parameterization for this Cartesian coordinate. If I started with my Cartesian coordinate, such that this is automatically satisfied. My equation of constraint are automatically taken care of. So once I do this substitution, with a being a constant, I no longer have to worry about this constraint anymore, because by redefining this, I am automatically taking care of the fact that this particle is moving on a circular ring. Similarly, if the particle moves on the surface of the sphere, okay, you have x1, y1, z1 for the first particle, and you just use your spherical polar coordinate transformation, and you can check by this similar use of this similar formula that things falls into place. So now you will see that this kind of so in this kind of transformation, my equation of constants are already taken care of, and I will employ my Lagrangian or Hamiltonian formulation, not Hamiltonian formulation, it's a bit more complicated, my Lagrangian formulation with respect to this coordinate. Okay, so the second problem of the second homework, I guess, was basically about this. Suppose we have found out that the Lagrange equation holds for the old coordinates, like the Cartesian coordinates. So you know that d dt of del x dot, or let us say x1 dot, minus del L del x1 equals 0. So these things hold for my Cartesian coordinate, let's say. What is the guarantee if I transform my coordinates via this kind of transformation rule? And now I say that my new coordinate is theta. What is the guarantee that my Lagrange's equation will still hold good with respect to my new coordinate system that I have defined as theta? So, so the second homework problem was basically to illustrate this point. So if you have found out that your Lagrange's equation holds for this old coordinate system, and you define a new coordinate system, okay, like this, and which are defined by this equation. So the Lagrange's equation will hold in terms of these new coordinates also, and that was the point of the second homework problem. So hopefully now you can understand what is meant by generalized coordinate and constraints a bit better, people who did not know it earlier. So you can tell me if there is any confusion in this stage.
Sir,
Yes.
sir, why you said before that theta is a dimensionless quantity here? Theta has a dimension of angle.
Angle is dimensionless.
Oh, okay, understood.
Okay. Anything else? Especially from people who did not who are not familiar with these concepts. Now, do you think the concept of generalized coordinates helps you a bit? I mean, I need an answer before I can proceed. Okay.
Yes, sir.
Yeah, yeah.
Yes, sir.
So for constraints, we just
Yes.
have to worry about holonomic, right?
Yes, I mean, holonomics are easier to deal with because they come in the form of this equality. For non-holonomic systems, you have to take like a separate route, which we will not bother about in this course. Okay.
Okay.
So the question you given is that holonomic? That is holonomic. Sir.
Definitely, that is holonomic. Could you identify the constraint there? Like, did you write down the constraint there? So I think the problem was like this. So it was a cone. It's not a nice cone in any way. So and the angle is alpha. So suppose a particle is moving in here. So if this particle is represented by coordinates x, y, and z. Will these x, y, and z be independent to each other? The answer is not, because if this is z and this length is square root of x square plus y square, then you can easily see that x square plus y square by z is equals tan alpha. So this is the equation of constraint there. Okay.
Yes,
So
sir.
not x, y, z are independent. So you choose your generalized coordinate wisely. Again, you choose your generalized coordinate wisely such that these are automatically satisfied. So yes, this is a holonomic constraint. Okay. Anything else?
But actually, I didn't know about the terminology of like holonomic and all, so I just wrote the equation.
No, you don't have to write out down the name. It's fine. If you do not know the nomenclature, it's absolutely fine. Okay, just make sure you understand what is meant by this constraint and how to deal with it. That is okay.
Yes, sir. It's like basically like one coordinate is depending, so we are removing its.
Yeah. So for this coordinate transformation, you just read the chapter of curvilinear coordinates a bit in more depth. You understand what are Jacobians, because these things that I am writing here is usually related to the quantity called Jacobian. I don't know if you have learned about this in your
Actually,
bachelor's.
like in the questions, like in simple questions like this, we can always use a line element to calculate the velocity, right? And then then we can like use it to find the kinetic.
Yes, you can usually calculate the velocity to using the line elements, but remember that sometimes lead to confusion because when you try to calculate the second order derivative, that line element doesn't straightforwardly generalize to that. Okay. So the thing I am trying to say is that so for example, you know the expression for del in Cartesian coordinate, right? So it's like del x x cap plus del y y cap plus del z z cap. Okay. Now you define your del square. Sorry. So let's say del in the spherical polar coordinate, and that would be simple, like r cap del r. So that comes from, because del r is the line element in the r direction. So perhaps this is what you were talking about. Then del y, I think it's del theta, r 1 by r del theta, because r del theta is the line element that in the theta direction, and in the phi direction perhaps it would be 1 by r sine theta del phi. Okay, so this intuition will work when you try to calculate del, but once you try to calculate del square, it will not work anymore. The del square is not just dot product with that. So you try it, and so that's why it's better to get used to the Jacobian formalism before so that you can, without any without any confusion, you can calculate these things. So given, so del square from here is just del 2 del x2. So del square in Cartesian would be del 2 del x2 plus del 2 del y2 plus del 2 del z2. But that will not be given like in a straightforward manner. By calculating del x, del y, del z, you will not be able to get the del expression for del square for spherical polar coordinates. Do you understand what I'm trying to get at?
Yes, yes, sir, I understand.
Yeah. So, yes. Anything else? Okay. So, if there are no further confusions regarding this, let me move on to the topic that that we started in last class, is a charged particle in an electromagnetic field. So the charged particle in an electromagnetic field. So I have a magnetic field which is given by del cross A, where A is the vector potential, and I have an electric field which is given by minus grad phi minus del A del T for a certain choice of phi and A. This phi and A are not unique, so I just say that for a certain choice of phi and A. Okay. By the way, before I proceed, are you familiar with the concepts of four vectors?
Yes, sir.
Okay. So should I take it as yes, or there are people who might be a bit? Yeah.
Not that much, sir, but a little bit.
In your mathematical physics course, has the chapter with tensor started?
Yes, sir.
Okay, that will help me then. Then, so you know what is meant by covariant and contravariant vector and metric
Yes, sir.
tensors. Yeah.
Yes, sir.
Okay, that's good. All right, that will do. And my Lorentz force law. Oops, I forgot where if there is a T here or not. Okay, I might be misspelling this. Lorentz force is given by F equals Q times E plus V cross B. Okay, that's my thing. And I will usually adopt a notation where I will put C equals 1. It's called natural unit. And when I will deal with quantum mechanics later, I will also put H cross equals 1. I will explain what do these things mean. So these are called my natural units. Natural units. What it means by that means is you are measuring all your velocity in units of c. Okay, so your velocity becomes dimensionless. So you mean if you say your velocity is 0.5, that means that particle is moving half the velocity of light, and you are measuring all your angular momentum in units of h cross. Okay, so if you say your angular momentum is 1, that means it's 1 times h cross. Okay, so these are what I mean by natural units. So you set h cross equals 1 and c equals 1 in all your expressions. Okay, that you get in your SI units. All right. So if so this is my force law. So let me write down the equation of motion here a bit. So I would write my d dt of mv, my this velocity equals which is the force, and that is q times v cross v. So q times q times e plus v cross v, q times minus grad phi, okay, minus del a del t. So that's your e. So that's your e. And plus v cross del cross a. Remember, our goal is to kind of figure out a Lagrangian that describes my Lorentz force law. So my goal is to find out a Lagrangian that describes my Lorentz force law. So I see that my equation of motion is this. Okay. Now, again, you can check that this thing, this V cross del cross A, so V cross del cross A, if you expand it and operate del properly, so that would be given by del V dot A minus V dot del operating on A. Okay, so it's from the vector identity, it should follow properly. So now if you go back to your equation of motion, you use this in the place of this. Okay, so now you have your equation of motion as d dt of mv equals q times minus grad phi minus del a del t. I will write this term first, so I will say minus v dot del operating on a and plus grad v dot a. Okay, so for now I want you to focus on this part only. So notice what is given, what it means. So if you try to compute this thing, del a del t plus v dot delta a. Okay. So remember, so notice this thing. So this will be del a del t plus V means x dot x cap plus y dot y cap plus z dot z cap, right? So I would write x dot del x plus y dot del y, if you prefer this notation, plus z dot del z times a, right? Now again, a is in general a function of x, y, z, t. So let me write down a is a function of your position. Okay, then if you apply the chain rule of derivative, then dA dt is del a del x x dot plus del a del y y dot plus del a del z z dot plus del a del t. Right? Now you compare with the above expression. Isn't it the same as this one? Okay. It's the same thing. So this thing here must be just my del a my sorry dA dt. So whatever I have is here. So with this insight, I can again simplify my above equation of motion here. So d dt of mv equals q times. So I will group first this term and this term here. So I would say minus grad of phi minus v dot a minus dA dt. Okay. So I take this term on the left hand side here. So I can write my equation of motion as d dt of mv plus qa equals minus q times grad phi minus v dot a. Okay. So this is a vectored equation. So this has three components. So the x component, y component, and z component. Okay. Let us focus on the x component first. Okay. And in general, it will have n component. So if I focus on my x component first, it reads d dt of mx dot plus qax equals minus q del x phi minus v dot a. So done for the x component, I got this one. Okay. So now if I compare, so my Lagrange's equation for this x component will be, I would say it would be d dt of del L del x dot equals del L del x. So kind of I map del L del x with this thing and del L del x dot here with this thing. Okay, it sounds reasonable. If I map that, then it will fit, right? So then this is del L del x dot equals would be given by mx dot plus q ax, and on the other side I have del L del x equals uh, minus del x of q phi minus q v dot a. I could have done it differently. Anyway, so notice this thing. So if I try to integrate it, okay. So if I try to integrate it, then I will get L equals m x dot square by 2, okay, plus q ax x dot. Now, since I am partially differentiating with x dot, then I can add a quantity that depends on the other things like y dot, z dot, and of course x, y, z. I can add these kind of things, all right? And here again, I have what do I have? L equals.
So we can include t now. Of function.
I mean, you can in general include t, but I am just trying to get the minimal one. Yes, in general you can also add t, right? Okay, but I am looking for the most minimal choice, but there is no t dependency. Okay, right? But you are right. In general, I can do that. Okay. So L equals basically minus q phi minus q v dot a. So minus q v dot a. So v dot a again is, sorry, plus perhaps this one. So v dot a is again ax x dot plus ay y dot plus az z dot. Okay. Again, you can do the same for the y component and in the z component, right? You just break it down and you will get similar expression. And then you try to figure out what is the minimal combination of L that satisfies all these things. Perhaps you can probably see that there is a one common term between these two, so which is this thing and this thing. Okay, so this is common in there, so this would be there. And adding these two terms, say y dot and a z z dot, does not affect my del L del x dot because I can always add to this one. Okay. Also, I should write perhaps here, I can add a function of x dot y dot z dot and y and z and t, because I am already talking about del x here. Okay, so I can add that. So that means if I add to this Lagrangian, so mx dot square over 2 can be absorbed into this part. Okay. And then ay y dot and az z dot can be absorbed into this part. Okay. So after all said and done, if you do the similar exercise for y and z components, you will see that your Lagrangian, the minimal Lagrangian that will satisfy all these derivatives would be half m x dot square plus y dot square plus z dot square. That is basically your kinetic energy minus q phi, because here was this q phi, and plus q v dot a. Okay. So that is kind of the Lagrangian that satisfies all the things. Okay. So I write it in a more convenient form. So I call it half mv square minus q phi plus q v dot a. Okay. So you now see that you cannot identify things as just t minus v. Okay, so t minus v is a bit is a bit obsolete, and if you identify this thing as your v, then it becomes a velocity dependent potential, and that's why we call it the potential is velocity dependent. So this is an example of velocity dependent potential, if you can call it even potential. Okay, if you like to call it in potential. As it happens, we do not call these things as potential. Okay, as we will grow up, we will see that the only kinetic part, so on the only kinetic part we call it the free Lagrangian. Okay, because the Lagrangian of a free particle only is the kinetic energy, and whatever is the other thing here, whatever is added to the free Lagrangian, we call it the interaction. It is perhaps called the interaction Lagrange. Now, there is an interesting neat bit about this interaction Lagrangian. First of all, so I was talking about 4 vectors. So the 4 vectors in the relativistic case then would read like this. So for example, let's say the position 4 vector is, for the contravariant one, is given by t, x, y, z, and the covariant one would be t minus x minus y minus z, which means I am working with my metric tensor, which I will denote by eta mu nu, is a diagonal matrix which is 1 minus 1 minus 1 minus 1. It has a signature of minus 1. Okay, so notice that if you go from covariant to contravariant, then you have to put the minus signs in front of your space components. Okay. Now, what do I mean by 4 vectors? 4 vectors is something that transform in the same way as this x mu does. Okay. And as it happens, I ask you to check these things. You can. Then the 4 potential can be written as the 0th component would be phi. Okay. And the 4 component would be a. That means this ax, ay, az. Okay. And the 4 current density j mu. So remember, 4 current density is so if you talk about the current density, let me say, so the current density, if you talk about, j is just rho times v, right? The velocity times this rho. And the J0 component of that would be basically just charge density. Okay. So again, I will suggest that even if you do not understand it right now, just check that this will be like this. So rho times say 1, and then v. Okay. So this is the 0th component of the charge density. Okay. Now, if you take this thing a mu, j mu, or rather the other way, it's more convenient. So this is j mu a mu. This is given by, if you calculate, this would be rho times phi minus phi dot a. Okay. And if I integrate over volume, so if I integrate over volume, and if these things are usually constant, let's say it's not locally distributed, then you can somehow see that this rho times dv, this rho times dv kind of features like q here. So here you see you have the same thing, this q v dot a, this thing. Okay, so the interaction Lagrangian that I have written here, it's a very naive way of explaining things. The interaction Lagrangian, which I call it L interaction, I think with a minus sign, I have written it as J mu A mu dV. Okay, so and you can write this thing as, this would be clear in the later part when I would be talking about classical field theory. So this thing, similar to charge density, I would later call it to be the Lagrangian density. All right, and the interaction Lagrangian density is just J mu A mu. Depending on how far you have been moved to the uh, to your electrodynamics course, you have perhaps been introduced to a thing called the electromagnetic field tensor, okay, F mu nu, F mu nu. And you have perhaps seen that this your all your electrodynamics formula can be obtained from uh, an equation. So del mu F mu nu equals J nu. I guess these are your Maxwell's equation. Okay, and this follows from a Lagrangian density minus 1 by 4 F mu nu minus J mu A mu. Okay, this follows from this Lagrangian density. So it's fine if these things are a bit alien to you, but I wanted to tell you that in the Maxwell's equation, you have already seen that this is the interaction term. So this is the free term for the photon field, that thing that I would be coming to.
J mu, A mu lowering.
Sorry, yes. Sure. And this is the interaction term. And this interaction term precisely comes from here. Okay. In the electrodynamics, perhaps you have seen it like a magic trick, but here you have a better feeling why J mu A mu should be the interaction. So this is the interaction of the photon with external currents. So if there are external currents present in your theory, then how should the photon interact, or how should my electromagnetic wave interact with external currents? And this is the thing. All right. So I will probably stop today's class here. And I understand that there might be questions in the last part. So you can go ahead and ask me.
Please once more say where how the constants are cancelled when we are writing the Lagrange. Yes. This line. I
How
couldn't
the
understand.
constants are cancelled?
Yes.
No. Nothing is cancelling. Okay. So when you solve your partial differential equation, okay, you
Yes.
add a function that is independent, that is explicitly independent of the variable that you are partially differentiating with.
Yes.
Okay. And so this is the same way. If you suppose I give you the result of a gradient of phi. Okay. Suppose I tell you that grad phi equals, say, I don't know what, say x plus y, whatever. Okay. And I tell you what is then phi x y z. Sorry, this doesn't make sense. X cap plus y
Yes.
cap. Okay. Then I ask you what is x y z. So then what will you do? You will first say del phi del x equals x, del phi del y equals y, and del phi del y del z equals 0. Then you will do this and you say that is phi equals x square by 2 plus one function that you call say
YZ.
a
Yes.
function of yz, and then you say del phi del y, so y square by 2 plus
So phi.
oh right whatever, and similarly with z, right? And now what you do is that since this can be a function of y and z, and you see that in the next solution you have a thing called y square by 2, so what you do, you absorb this y square by 2 into here, and you write your phi is basically x square by 2 plus y square by 2. So what you do is you absorb x square by 2 into this constant and y square by 2. I don't know in what language you express this thing, but that's how I try to express. So is it a bit better now?
Yes, sir. But here, then here plus FZ. No.
Here.
Yes, in this example.
So
There
phi
is
would be some constant. Let's say I call it c plus the constant is immaterial in any way. Okay, and this is fz yx, right? So I can absorb both these things. The y square by 2 can also be absorbed here, and x square by 2 can also be absorbed here. That's it. There is no new things.
yes, but there should be a constant.
Doesn't matter. I mean, in
Okay.
the Lagrangian things, there is no, I mean, no point of carrying forward a constant.
Yes. Understood, sir.
Okay. Anything
Yes,
else?
sir.
Yeah.
Sir, you define that Lagrangian density and integral over a volume.
Yes.
If I integrate out over the entire volume, even a small amount of J mu d mu will blow up. Then how can
No, those J mu's would be vanishing at the boundary. That's
Okay.
how you use conservation of charge, right, from equation of continuity.
Yes, sir.
Okay.
But,
So
J,
you remember this del
yes,
dou del t?
divergence of J0.
Okay. So from this, how do you get your conservation of charge? What is the next step you do? By the way, this can be written as del mu J mu equals 0.
0, yes.
Okay.
So
So yeah,
then I
tell me.
integrated on and considering the fact that J at boundaries is 0.
Exactly. So these J's are localized charge distribution.
Okay.
What I mean, yeah. So these are localized currents.
Okay, sir.
Okay.
Okay, sir.
Mhm. So anything else? By the way, in electrodynamics course, did these things like did the instructor arrive at this point yet?
No, sir.
No, sir, not yet, sir.
All right. Okay. So wait for that. So you have not been introduced to F mu nu yet. You do not know what is electromagnetic field tensor.
No, sir.
Sir,
Okay. All right. I understand. But okay, I will give a homework so that you can do it yourself.
okay.
It's not very difficult.
Okay, sir.
All right then. So if there are no further questions, let me end the session here, and I will see you tomorrow. So stop.